Right, okay, so this time it's a three-phase unbalanced delta. Connected load comprises of the following impedances, and you've got all your impedance there given in rectangular form and in polar form. Again, it's really the polar one that we're interested in because that's the one that gives you the magnitude. So you're really interested in these magnitudes, not really in the rectangular form. It says calculate the total apparent power at the load when it's connected to a 400 volt three-phase supply. So 400 volt, so your V line is 400 volts, and because it's a delta, there's no change. If you remember what a delta looks like. But your VL and your V phase are the same. So because it's a delta, if your line's 400 volts, then your phase is 400 volts. So the other thing to maybe take a wee note of just now is in these three impedances, your plus J's and your minus J's. So your plus J's, they're inductive, aren't they? So plus J's are inductive, so that is lagging. Minus J's are leading, they're capacitive. And this will make a difference in terms of your Q, because your Q's don't just add up the way that P adds up. Your Q's add up, taking into account the difference between leading and lagging. But we'll get a wee bit more to that as we kind of go on. So we've got our three impedances, we've got our phase voltage, which is the same as our line voltage, so now we can go on and do our currents. And we're just using our magnitudes again. Magnitudes only, that's why I've kind of picked this method, because you don't have to bother.
Okay, cool.
56.58. We're going to do the same for I2, using Z2 this time. So it'll be 400 over 10. And for I3, 400 over 10.77. And that's your three currents that you're interested in. So now we're going to pretty much use the same method as we used yesterday. And we're going to get P1, if you like.
I can't see it on there.
There you go.
Thank you.
So that'll be your 400, because your V phase is the same as your I phase. Your I1, 56.58, times cos of your angle. Now your angle, you take this from here. Don't take the negative, just take the size. So it's from there. Not take the negative, just take the size. I'm just going to round that to 16 kilowatts, I think that's fine. I'm now going to go in and do Q1 and S1. Formula for Q, VI sine of the angle. And that's 16 kVAR. There's kind of no point doing S, but I'll kind of explain that a wee bit later on, once we've got through our P's, Q's for all three. So now if you want to go ahead, work out P2, Q2, P3, Q3. Bear in mind that Q1, because that first impedance is leading, that Q1 is going to be leading. So you put in your leading with that Q1. So now if you could work out P2, Q2, P3 and Q3. I'll put in what your final answer should be. Oh, I made a mistake. I made a mistake. And these should be the values you should get. So when you look to get your total power in terms of true power is easy enough. You just do P total and you just add your P1, your P2 and your P3, 3 phases. Quite easy. So 16, 9.6 and 5.52. It's 31.12 kilowatts. Your Q total is a wee bit different. So the reason we were thinking so much about leading and lagging, if you were to draw, I'll use this bit of paper over here. If you were drawing your power triangles, it doesn't matter which way you decide, but you would always draw leading and lagging in opposite directions. So if you decided that was your convention for lagging, then that would be it for leading, going in the opposite direction. So your P's add up, just going straight along that kind of horizontal axis. But your Q's, lagging Q's will take you down, leading Q's will take you up. So when you look at your Q's for your answer, lagging Q's will take you down, leading Q's will take you back up again. So this one, looking at it, is clearly more leading than lagging, isn't it? You've got two leadings, one's 13, one's 16, so you're kind of thinking, well, that's like 29, and then you're lagging, you've only got 12. So, overall, you know this is going to overall be leading. So I'm going to do Q1 and Q3, my two leading Qs, and I'm going to take away Q2, my lagging Q, because I know overall I'm going to be leading. No, I've got to fill off the side of my page. And that's kind of the reason why it doesn't make any sense to work out the S's, because the S is going to be the hypotenuse of that overall triangle. So this is going to be overall leading. So when you go to work out your total S, I'm going to use that P and that Q in a triangle. I wonder if I've got a ruler in my bag. I don't think I have. Now, true sketch. You get a protractor? Lovely. Right, okay, so pick a scale. Halves. So I'm going to use this big page over here. So your P always goes horizontally. So that's my P, and my value for P was 31.12. If I'm going leading by the convention that I decided earlier on, leading takes me up the way. 17, half of 17 is 8.5. You take me up there. That's my leading Q, 17 kVAR. Exactly 17 kVAR. Leading, which is why I took the direction up that way. And then my S is a nose to tail of that P plus the GQ, if you like. So that'll be my S value there. So from that triangle, that'll be my circuit phase angle as well, or my three-phase phase angle if I want to work that out. So to get my S, I'm just going to use Pythagoras. No, by Pythagoras, S squared, which is the hypotenuse, P squared plus Q squared, and that's me 1257.4544. So my S is going to be the square root of that. So the root of that answer gets me 35.46 kVA. And that's it. So that's the total apparent power. And your power triangle to work it out. So to kind of recap what you need to do, when you start off, when you look at your question, you want to make sure that you've got all these impedances in polar form and that you've identified whether or not they're leading or lagging. So that's the first thing you do. Now, if it's a delta, you use the voltage as it is. If it's a star, you divide that voltage by the root of 3. Okay, so delta, leave it the same, star, divide it by root 3. Then work out your 3 currents just using the magnitudes, using whatever that voltage is, depending whether it's a star or a delta, divided by your 3 impedances in polar form. Then work out your P and your Q using your V, your I from the list, and your angle from your impedance. Drop the negative sign and just keep a note for your Q's of whether they're leading or lagging. Your P's add up, just going straight across to the right, and your Q's, take your leadings as being positive, take your laggings as being negative, and get an overall Q from that. Then take that P and that Q into a power triangle to work out S. I can't see that they would ever ask you for the overall angle of the 3 phases, which is why I've kind of went, I'm not going to bother doing that. Just from a purely maths point of view, of course you can work it out, but I don't know that there would be any real reason.
Right.
So I don't know that there's any point. Obviously you could do it, you just use SOHCAHTOA, but there isn't a reason. And that is that.